Okay, so let's move on to the last example of the week, which is related to estimating confidence level. So what is confidence level? You probably learned from your first statistics class there's something called confidence intervals. So suppose that theta is our parameter of interest, which describes some characteristics of the distribution x. Then, given a random sample from x1 up to xn, a confidence interval of theta takes the form of the interval from u to v, where u and v are the corresponding upper and lower bounds. The lower and upper bounds for the interval. You should note that here, both u and v are functions of the observed data. So based on your samples, you try to find out what is the confidence interval. So you just apply some kind of transformations of your samples and get the upper and lower bounds. The confidence level of the interval u to v is the probability that this interval covers the unknown parameter of interest theta, so the true value theta. We usually denote this by 1 minus alpha or 1 minus alpha star, where alpha star is the desired level of type 1 error rate we want to achieve. We'll talk more about that next week. So the confidence level 1 minus alpha star is given by the probability that u is less than theta, which is less than v. In other words, the true theta value lies within this confidence interval. Thus, you can see that since this is a probability, so the confidence level is a probability that involves some random variables, it's essentially an integral problem, which we again can solve using Monte Carlo integration or Monte Carlo estimation. So how can we numerically estimate the confidence interval? This is actually, again, very similar to what we did before for the other two cases. So estimating mean and estimating MSE. We are going to draw we are going to do a total of m replications. So for each j between 1 and m, we're first going to draw the x values, so our random samples of size n for the jth replication. These will be drawn from the distribution x. And next, we can compute the corresponding uj and vj, which are the upper and lower bounds for the confidence interval based on this set of random samples. And then from there, we can compute whether the true parameter theta we're interested in is actually within this confidence interval. So again, we apply the indicator function to find out yes or no. Then you can see that 1 minus alpha is equal to the probability that u is less than theta and it's less than v. So this is equal to the expectation of the indicator function applied to testing whether theta is between u and v. And because this is again an expectation, this can be estimated by the sample mean. So we have drawn m samples of this, so indicator of theta between u and vj earlier. If we take the sample mean across the m replications, we get an estimate of this confidence level. So let's see an example which involves finding out the confidence level of Bernoulli proportion confidence intervals. So suppose that x follows the Bernoulli distribution with probability p. So here p is the parameter of interest, which is the probability of a success. We want to find a 95% confidence interval for p. So if this is our task, it might bring up some earlier memories for you where you say, wait a minute, I learned about how to do this. So suppose x1 and xn are random samples of size n from X that you might have learned from a early statistics class that a 95% confidence interval for P will be given by this over here. So the lower bound U will be equal to P bar minus 1.96, which is the Z value corresponding to the 0.975 quantile under standard normal distribution, times the square root of P bar times 1 minus P bar divided by sample size n. And the upper bound is very similar, except we replace the minus with the plus. So this confidence interval works when our sample size n is large. This is essentially again applying the central limit theorem. And by the way, here P bar is the estimated sample proportion or the observed proportion of ones in our data. And that's given by the sum from 1 to n of the xi's, where xi is either 1 or 0, divided by n, so the observed proportion. So this interval works. The confidence interval works if we can apply the central limit theorem. But we know that the central limit theorem is a large sample result, so our n needs to be sufficiently large. However, what if our n is not sufficiently large? If we obtain this confidence interval, what is going to be the true confidence level that is associated with the confidence interval? In other words, if n is not very large, then what is the probability that this interval actually covers the true P? Let's try to find the Monte Carlo estimate of the confidence level for different sample sizes and different true P's. We'll try the probability of successes between 0.1 and 0.9. So 0.1, 0.3, 0.5, 0.7, and 0.9. And now let's consider a relatively new question. Earlier, we just assumed that we're going to just get a large number of draws. So let's just pick M to be something really large, like 10,000 or 100,000 or something larger than that. However, a question you might have in practice is how many replications do you want to do? So what is the M that you will need if you want to achieve a pre-specified level of standard error? In other words, how can we choose the number of replications M if we want the standard error of our confidence level estimate to be less than, say, 0.0005? This is a very practical task because, so the Monte Carlo estimate you get at the end is going to have some random fluctuations. Sometimes you will want to control the level of random fluctuations and ensure that it isn't going to be too large to affect your decisions that you make based on the Monte Carlo results. At the same time, you might want to save some computing power, and you don't want to draw, say, 1 million samples because that's probably going to take a lot of time, especially for more complex tasks. So sometimes you want to determine what is an appropriate M so that it's not going to take you too much computing power, but at the same time, you achieve the level of accuracy you want. So how do we choose M? Notice that here, each of our indicator function applied to this thing, so whether theta is in the corresponding interval, is actually a Bernoulli random variable with success probability 1 minus alpha star. So 1 minus alpha star is the true confidence level that we're trying to estimate using Monte Carlo techniques. Each of these, so whether theta is within this, will be equal to 1 with probability 1 minus alpha and equal to 0 with probability alpha star. So you can see that our Monte Carlo estimate, which is the sample mean of M of these Bernoulli random variables, will have a standard error that is equal to the square root of 1 minus alpha star times alpha star divided by m. So you can see that here the standard error will depend on the true 1 minus alpha star that we are trying to estimate. If you expect the estimated confidence level 1 minus alpha star to be around 0.95, then you can plug in 0.95 into this equation and try to find out what is the m value that will achieve a standard error below 0.0005. I think I'm either having too much of zeros here or having one less zero here. I think this should be 0.005. Sorry. So you can try to solve square root of 0.95 times 1 minus that. So 0.05 divided by m is less than or equal to 0.005. And you'll be able to find that m, the number of replications you want, will need to be greater than or equal to 1900. However, alpha star is the thing we're trying to estimate, and sometimes we cannot be so sure what value it is around. So if you expect your alpha star to be close to, say, something around 0.5, so the confidence level to be around 0.5, or you have completely no prior knowledge about what the true confidence level is going to be around, then it might be safe to choose an m that is more conservative. So in this case, you can choose an m so that the maximum of this thing for any possible alpha star value is less than or equal to 0.0005. And you'll be able to find out that this standard error estimate is going to be maximized when alpha star is equal to 0.5. So when your true confidence level is around 0.5, and the corresponding m value needs to be greater than 10,000. So let's be conservative for our current simulation studies, and we will use this one. So we will use a m equal to 10,000. Okay, so let's get started with estimating the confidence level for the Bernoulli proportion. To implement this, we need to first, for j from 1 to m, do the following. We first draw n Bernoulli samples, x1 all the way up to xn, each with success probability p. So recall that we're going to play with different sample sizes and possible p-values. But in general, given an n and a success probability p, we're going to first draw the Bernoulli samples, x1 to xn. And then giving the samples for iteration j, we want to compute p bar as well as the corresponding confidence interval. So if we use the earlier formula, you know that the confidence interval, the 95% confidence interval, will be given by p bar minus 1.96 times the square root of p bar times 1 minus p bar divided by n. P bar plus 1.96 times the square root of this thing. Then after we obtain the confidence interval given the jth random sample, we will test if the true p-value is covered by this interval. So the result will be either true, where p is within the interval, or false, where the true p is actually outside that interval. The Monte Carlo estimate of the confidence level, 1 minus alpha star, is then given by the proportion of times that p, the true probability of success for the Bernoulli draws, is within the confidence interval. So we'll store our estimated confidence levels in a matrix. I haven't talked about this yet. So what are the sample sizes we'll play with? So we mentioned that there are two conditions we'll try to manipulate. The first is the probability of success, which ranges between 0.1 and 0.9, increasing by 0.2. And then we'll also play with the sample size, which is the sample size n that we use to get p bar and to approximate this confidence interval. So the possible sample sizes are 10, 25, 50, 100, and 500. You will expect that for some smaller sample sizes, the confidence interval based on the central limit theorem isn't going to work quite well. However, as we increase the sample size, the resulting true confidence level might get closer and closer to the theoretical 95%. And like we mentioned before, we're going to use m equals 10,000. Let's first create an empty matrix, conf level, where the number of rows is equal to the number of possible p's. So 0.1, 0.5, all the way up, 0.1, 0.3, all the way up to 0.9. There are 5 possibilities, so there are going to be 5 rows. The number of columns is equal to the number of possible sample sizes. So you can see that for each entry of the matrix, we're going to store the results on the confidence level for the corresponding p and the corresponding n. Here's the code for getting the results. We're going to loop over all possible p's and n's. And under each of these p and n condition, we are going to draw the confidence level for a confidence interval for m iterations and test whether the true p is within this confidence interval. We first create an empty vector of length m called inconfint. This will, as the name suggests, be a 0, 1 vector, which tests for the jth iteration between 1 and m. Is the true p within the confidence interval that we have calculated. So we're going to loop from 1 to m. And for each of these j's, we first find our Bernoulli draws. So we first draw n samples from the Bernoulli distribution. So binomial size equals 1 is just the Bernoulli distribution. Number of samples we draw is equal to the nth entry of the nth vector. And the probability of success is given by the pth entry of the pth vector. After we get our Bernoulli draws, we'll be able to find out p bar and the corresponding u and v's. So p bar is just the mean of x, our draws, and u and v are calculated based on the earlier formula. Lastly, we test whether the true p, that's the pth entry of the pth vector, is within the interval between u and v. So we do 1 times p is greater than u and p is less than v. If both of these are satisfied, this will be equal to j. It will be equal to 1. So the jth entry of inconfint will be equal to 1. If either of these are not satisfied, it means that our p is either greater than or equal to v or less than or equal to u. This means that it's outside of the interval, and this will return 0. This is essentially the indicator function. The last step will be computing the mean of the indicator functions. So for the p and n value, for the particular p and n value, the confidence level is going to be the mean of the inconfint vector. So the proportion of times the true p is within this interval. And here are the results. So like before, let's first give the conf level matrix row and column names. As we described before, the rows of the matrix will correspond to different conditions of proportion and probability of success. So the possible p's between 0.1 and 0.9. And the columns will correspond to different conditions of sample sizes. And here are the results rounded to 3 decimal places. You can see that here when n is large, so when n gets to something like 100 or 500, then no matter what your true p value is, the resulting confidence level is quite close to the theoretical level of 0.95. So for larger sample sizes, the central limit theorem will apply better to our observed data. However, when the sample size is small, then especially when the probability of success is at the two extremes, so when p is 0.1 or 0.9, we can see that the true confidence level is quite far from 0.95. For example, when the sample size is 10 and the true probability of success is 0.1, the confidence interval we got actually just covers the true p around 65% of the times, not 95. The same for p equals 0.9. And we can see that in general, when p is in the middle range around 0.5, even in small samples, when n equals 10, the confidence interval covers the true p 89% of the times. So it's slightly better than the two extremes. So this is one way Monte Carlo techniques can be used to help you verify the results of some kind of sampling distributions, asymptotic distributions that you have developed.